Hello, I am Oscar Cornejo from the SMT Research Center of the University of Luxembourg, and I am going to present our tool MAS for mutation analysis of space cyber-physical systems. This is a joint work between Fabrizio Pastore and Lionel Briand. In today's presentation, I am going to introduce one of the results of a project funded by the European Space Agency that aims at assessing the quality assurance practices and how to improve in them. This project involves Workspace Luxembourg, which is a developer of nanosatellites, and Workspace, who develops microsatellites. Our findings and tools can be found at facwas.uni.lu. The motivation for this project lies on the fact that software has a prominent role in space systems, and consequently, software failures have high impact, ranging from explosions to loss of a large amount of data. Therefore, it is of paramount importance to thoroughly verify and validate space software. But how it is done nowadays? Software testing is prevalent in validation and verification because it's the most scalable approach. Engineers develop a number of executable test cases that exercise the software under test and fail if the software does not meet its specifications. Each test case sends a number of inputs to the software and verifies that the software produces an output that meets its specifications. But how to ensure thorough testing? How to ensure that the test suite exercises all the functions of the software? A valid solution is mutation analysis. It consists of automatically generating faulty versions of the software under test that are called mutants. The mutants are tested with the test suite for software under test. The mutation analysis metric is the mutation score, which is the percentage of mutants leading to a test failure. Ideally, all the mutants should lead to a test failure, but in practice we may have mutants that are equivalent with the software under test and other mutants that are redundant within each other. All of these affect the pertinence of the mutation score as an adequacy metric. Also, the presence of a large number of mutants introduces scalability issues, especially when the test suite takes hours to execute, like in cyber-physical systems. The literature presents solutions to the problem I just mentioned, but most of them are not applicable. In general, there are several optimization techniques, but we lack work evaluating their integration. Scalability solutions like mutant schemata and split stream execution can work with ad hoc emulators. Mutant sampling approaches either do not provide guarantees about the accuracy of the estimated mutation score or require too many mutants. Some prioritization solutions make sense only for unit tests, while others rely on expensive data flow analysis. The identification of equivalent mutants based on symbolic execution is practically infeasible with large systems. Instead, dynamic analysis approaches collect too much data. Finally, work on redundant mutants show that it's better to keep subsumed mutants but improve the test suite to distinguish them. Therefore, we simply focus on detecting duplicate ones. Instead, we have developed a toolset that implements a pipeline that we call Mutation Analysis for Space Software CPS, MAS. In the next slide, I will introduce our approach. In the first step, we collect code coverage information from the test suite. In the second step, we create mutants, but only for the coverage statement, under the assumption that there is a reason for a statement not to be covered. We rely on the operators indicated as effective in the literature, which are the sufficient set, the OODL set, and the LVR operator. In the third step of the methodology, we just compile the mutant. In the fourth step of our methodology, we remove equivalent and duplicate mutants based on compiler optimizations, which is standard practice. We compile the software with all the available options. For instance, in GCC we have O0, O1, O2, O3, OS, and OFAST optimization options. Then we compute the hash summary for each generated executable, And to detect equivalent, we compare with the original software, while to detect duplicate mutants, we compare pair of mutants belonging to the same source file. Then, in the fifth step of our methodology, we are going to sample the mutants that we are going to execute. So, to do this, imagine that we have a true mutation score of 65.36. When performing mutant sampling, the estimated mutation score will vary based on the number of mutants being sampled. With a large number of mutants being sampled, we will obtain a mutation score that is close to the actual one. Of course, we may have variations if we repeat the experiment other times, but the point is that we would like to stop sampling when we are close enough to the actual mutation score. We have developed a method to determine when we are close enough to the mutation score based on the computation of a confidence interval. A confidence interval captures a range that has a probability, around 95%, of including the estimated value, in this case the mutation score. Basically, the mutation score can be represented in terms of an interval with an upper and lower bound. What is returned to the user is the value in the middle. This determines when to stop sampling, and to do this we rely on a fixed width sequential confidence interval method that we call Fsci, which means that we stop sampling when the range is small enough. In our case, we stop when the range is below 10 percentage points, which means that the mutation score returned to the end user should be at most 5 percentage points far away from the actual mutation score. This, of course, assuming that the mutation score follows a binomial distribution, and for this we rely on the Cooper-Pearson method to compute the confidence interval. So basically, this is the loop that we execute to sample the mutants. We execute test cases, we evaluate the mutation score confidence, and we sample additional mutants if the range is not small enough. However, we are going to execute a subset of test cases. I will explain later how, but since we sample the mutant, we may exclude the test cases that kill a mutant, which means that the computed mutation score might be lower than it should be. So we have to introduce a confidence interval correction factor. Without going into the details, the mutation score can be accurately estimated only after adding the proportion of mutants that are alive because of mistakes in the test suite selection. Therefore, we estimate the proportion of mutants that are alive by mistake. We then compute the confidence interval by adding the lower and upper bound of such proportion. Now, let's see how we prioritize and reduce the set of test cases to be executed. For test suite prioritization, we rely on statement coverage information. We have a greedy algorithm that selects first the test case with the largest distance from the closest test already selected. As a distance function, we demonstrated empirically that cosine distance is the one providing the most accurate results for the mutation score. In the step number 8 of our pipeline, we discard likely equivalent mutants by disregarding those mutants that do not show a difference in single coverage with respect to the original program. Finally, in the last step of our pipeline, we compute the mutation score by considering the live non-equivalent mutants and the killed mutants in order to produce a final score. Now, I will present a demonstration of our tool. For this, we will apply MAS to evaluate a test suite for a data encoding library provided by the ESA. The library has been generated from a data model specified with the ESA1 grammar. The test suite has been generated automatically from the same data model. The size of this software is around 2,800 lines of code, and the test suite consists of 107 test cases. To install the MAS workspace, we're going to move into Facua setup folder. MAS requires to define the variable install dir. In this case, we have selected opt ICSE demo. Inside this folder, we will find all the launchers and configuration files required for the execution of the tool. So, after installing MAS, what we are going to do is to configure the software. So, we see that we need to provide some paths in order to make MAS work, such as setting the directory path where MAS file can be stored, the type of built-in system that we're going to use, the root path of the software under test, the path to the test cases, the path to the coverage files, also the file name of the compiled file library, the path to the original makefile, the compilation command, the cleaning commands that are necessary for optimization. Then also we need to provide information for MAS, such as if we are going to use MAS in an HPC, the trivial compiler optimization that we're going to use, if we need our test suite to be prioritized, and the type of sampling. In this case, I have set up for Fsci sampling, which has been demonstrated to be the most effective one. So, after configuring MASCOF, what we need to do is to configure mutation functions. As the name says, we need to provide implementation for running a single test case, and it should return 0 if the test case passes, or otherwise it should return 1. So we're going to provide the command for a single execution of a test case, and then we are going to make a return. The last step for configuring MAS consists of providing a bash script that will collect code coverage information and the compilation instructions. Okay, so we need to execute in a for cycle all the test cases one by one, and then we need to invoke the FACAS code coverage script and to pass the name of the test and the time consumed for a single test execution. The first step of the pipeline consists of executing the prepare suite script that collects effectively the code coverage and the order of execution of the test cases. So after executing, we are going to go to the COV files folder, and then we will see that there will be a test suite order file that stores the order and the timeout for each test case. Then we will see that a single folder for each test case collecting the source code and the code coverage information for a single test case. The next step of the methodology consists of generating the mutants. For this, we will simply invoke the corresponding MAS launcher generate_mutants.sh. At the end of this step, all the mutants will be stored in the source mutants folder. As you can see, in the source mutants folder, we have created all the mutants for the system under test. If we open this mutant, we will see that in line 642, we have applied a ICR operator to replace the number at the end of this statement. The next step of the pipeline consists of disregarding equivalent and redundant mutants with trivial compiler optimizations. To this end, we store the hashes of the compiled mutants for all the optimization levels. After compiling the mutants, we process the hashes to identify equivalent, redundant, and also non-compilable mutants. As you can see, we have generated a list of the compilable and non-equivalent, non-redundant mutants that is called all filtered. The next step of the pipeline consists of generating a prioritized and a reduced test suite. For this, we are going to use the generate pts.sh script, and it will take a while to analyze each statement of the source under test. This step will generate a file containing for each mutant a specific set of tests to be executed in a specific order. So for instance, for line 103, we see that the order will be test 75, test 27, and test 4. Then for the prioritized suite, we will see that for the same line 103, the order would be test 75, 27, test 3, then test 74, test 4, and test 26. Then we will execute a subset of the mutants. In this case, we have decided to use the Fsci sampling approach, which means that Fsci determines the sample size dynamically while exercising mutants, based on a fixed width sequential confidence interval approach. During this step, we will collect, in addition to code coverage, the mutation traces that include the mutant statuses, the test executed, and the execution times. There will be one line per test executed. As you can see, for this mutant, we have executed the test 28 that has been killed. Then for this mutant, instead, we have several tests executed. In the next step, we will identify equivalent mutants based on code coverage. In particular, we compare the coverage of the original program against the coverage of the live mutant. The mutants that do not show a change of code coverage will be considered likely equivalents. The mutation results will be updated accordingly, removing the equivalent mutants. As you can see in the image, we provide the list of likely equivalent mutants because the distance between the mutated version and the original version is 0. As you can see, we also provide a list of useful mutants to be analyzed by the engineer. The idea is that these mutants behave differently from the original version of the software and they were not detected by the test suite. In the last step, we generate a mutation report, which shows the mutation score, the number of mutants sampled, the code coverage, and shows a pointer to the list of live mutants to be analyzed by the engineer. So, we have seen that in our example, we have generated a total of 8,636 mutants. 2,000 of them were considered equivalent or redundant by trivial compiler optimizations. We analyzed 706 mutants with Fsci sampling, 360 are killed by the test suite, 340 were not detected by test suite or they were live mutants, and 265 were considered likely equivalent because these mutants didn't show difference with respect to the original program in terms of code coverage. Then the mutation score for this test suite is around 82%. To show the usefulness of our approach, I present an example of a shortcoming of the AS1 test suite exposed by mass. Here we have a mutant affecting the line 1298 and it is particularly modifying the 0 on the ternary expression by a -1. This is done by the operator ICR on the function t int is constraint valid. So, investigating a little bit on the function under test and the test suite, we found that the problem is that the test suite is not verifying the value of p error code. In fact, the value of this variable is being rewritten 3 lines below the yellow line. In this case, will be enough to verify the p error code variable along the red variable within the if expression. We have presented MAS, a tool that makes mutation analysis feasible for space software and in general for large embedded software in CPS. Our aim is to support both software developers and regulatory agencies performing independent verification and validation. MAS can effectively apply on large space software. It reduces the processing time of mutation analysis by discarding equivalent and redundant mutants, sampling a subset of the mutants without affecting the accuracy of the estimated mutation score, and prioritizing and reducing test suites. We also presented a live demonstration of MAS applied to the AS1 case study system, where we detected a shortcoming of the existing test suite. Thank you very much for your attention.